Good morning. Okay, so we're in Chapter 5 now, and in a way you've already been introduced to the main idea of Chapter 5. When we were working with the Venturi meter last week in the lab, you had to apply the principles of continuity in order to find the velocity of the water through the nozzle. In fact, we did that the week before that with the flow visualization, because you knew that there was a certain tube that had a 1 centimeter diameter and went through the process of finding the velocity in the tube in order to find the Reynolds number. So Chapter 5 should seem very familiar to you as we go through it. Just an announcement here that this homework assignment is due a week from today. All right, so we'll begin by taking a look at a reservoir up on the border of North Dakota and South Dakota. It's the Oahu Dam, and it's on the Missouri River, and it's the 4th largest artificial reservoir in the United States. It's absolutely enormous. It's owned and operated by the Army Corps of Engineers, and it was put into place for a lot of different reasons. For one, they use it for flood control, so that when there are big, heavy peak storm events, that it doesn't cause flooding downstream at quite the same extent that it otherwise would. Another advantage of this dam is that it's being used to generate electricity. And so overall, the benefits, when you quantify the electrical generation and the flood control that it's able to do, and they sometimes try and put a dollar value with additional recreational opportunities that a reservoir will afford. You know, people go fishing and tourism, that sort of thing. So overall, $150 million a year in benefits this dam and reservoir are able to generate. So let's take a look at, zoom in. You can see here are some agricultural areas, and another advantage of a reservoir is that it sort of provides for more regularity in irrigation. Here's a zoomed-in view of the dam, and this is the intake structure that feeds water to the power plant. There's a tunnel that transfers the water to the power plant, and most of the time that's where the water comes out of the reservoir. It's through this tunnel and to the power plant. When there's really a lot of precipitation in the watershed that's upstream of this reservoir, though, there's too much water and they can't accommodate all of the flow through the power plant. And so some additional water has to be put through these emergency release gates. Now here's a view of the power plant. And one of the heaviest storms that they've had in recent times up there at the Oahu Dam was in 2011. There was heavy rainfall that made it necessary to release 160,000 CFS. That stands for cubic feet per second. And you know, sometimes numbers like that don't really make any physical sense, because when you're dispensing water into your bathtub, it's not in terms of cubic feet per second, and you don't have a meter on there anyway. I mean, we maybe think about what a gallon per second would be, or a liter per second, because those are volumes that we deal with on a more regular basis, but a cubic foot per second. So just to put it into perspective, how much is this 160,000? I'll open up a news release that was put out last year that was explaining how much water they were going to release on the Gauley River during whitewater season. And so maybe it's a little bit hard to see. So I couldn't find this year's report, but last year during Gauley season, who here has ever gone whitewater rafting on either the New or the Gauley? Some of you. I've done both, and it feels like it's a lot of water. I mean, it feels like, wow, massive quantities of water. You're really on the verge of sinking, and it's a dangerous thing. That's less than 3,000 CFS. So back to this map view. There was 160,000 CFS that had to get out of this reservoir, and it had two ways to do that, through the power plant and through the release gates. And so the power plant has a maximum of about 50,000 CFS. So that's how much flow they can accommodate through there. and the rest of it has to be put through these spillway release gates. And they're enormous because they really don't want the water levels to get so high that the water is flowing over the top of the dam. Anyone take a guess on why that would be considered a bad thing, to have the water just spilling over the top? That's right. It could erode the soil. There could be scour. And sometimes they'll have a specific location where there's an overflow spillway that's armored with concrete, and there's a lot of riprap at the bottom to try and dissipate the flow. And so they anticipate the possibility the reservoir could fail. But in this case, if you had 110,000 CFS just flowing over the top of that reservoir, and if we look at it, it's soil. You know, there's a soil surface there that would be eroded. And so these release gates are huge, 19-foot diameter, and there are 6 of them. So just to get a feel for these magnitudes, let's calculate what's the water velocity through the gates. And to whet your appetite for that example, pardon the pun, pretty awful, right? Puns are the lowest form of humor, as they say. Here is a view of the event itself. That's kind of pretty, right? So we get a view from different angles, and you get a sense for how much energy, is being dissipated there. That's a lot of turbulence. And that's intentional. They want to dissipate as much energy as possible prior to the water getting back into the Missouri River, because this is an engineered location where they have a spillway that is armored with high-strength concrete that's reinforced, and it's going to be able to absorb the energy of all of this water moving very quickly. But if they allowed the velocities to stay high as the water moved downstream of this overflow spillway, then it could cause a lot of scour in the river, and that leads to deposition downstream, where it could clog some of the locks and dams like we have here in the Huntington area. They have locks and dams and hydraulic structures downstream that they don't necessarily want a bunch of sediment clogging up. So they try and have as much energy loss as possible in a certain location. In hydraulic engineering next semester, the civil engineers among you who will stay with me next semester, we'll talk about hydraulic jumps and how that's used as one way of dissipating energy. But just to give you an idea of the magnitude of how much water was being released, I think this video does a pretty good job of illustrating that's a lot of flow. But the velocity, so look at it. You can't really tell just visually what's the velocity of the water. It seems like it's moving quickly. You wouldn't want to jump in there. I mean, maybe if you had like water wings on, then you could do it, right? Or a surfboard. All right. So let's consider this example. What is the velocity through the gates? So we know the flow rate, this 160,000 CFS, that's Q. Q, or flow rate, the volumetric flow rate, has units of cubic feet per second. And what we want to find out is the velocity, which has units of feet per second. And so the relationship between Q and V is Q equals V times A. Velocity times area gives you volumetric flow rate. And we can tell that area, if it has units of square feet, you multiply square feet by feet per second, and it gives you cubic feet per second. All right, so in this example, you're going to have to assume that the flow goes through these 6 gates equally. It's divided equally among the 6 gates. You'll need to calculate the cross-sectional area based on the diameter that's given. Those release gates are circular. That's why their dimensions are specified as a diameter. So see if you can calculate the velocity. Okay, so there's 160,000 CFS that's coming out of the reservoir. 50,000 of it's going through the power plant, which means 110 is going to be going through those spillways. There's 6 spillways, and so each one of them is receiving 18,333 cubic feet per second. We need to calculate the cross-sectional area of each spillway pipe based on its 19-foot diameter, which is enormous. And think about those gates when they're closed, 19 feet in diameter. And that's way taller than this room. Velocity ends up being 64.7 feet per second. Just to put that in perspective, maybe a rule of thumb would be 20 feet per second is kind of an upper limit that you wouldn't want to exceed unless you really put some careful thought and planning into armoring the concrete. You know, if you just had water that's flowing down a spillway 20 feet per second, and you're sort of getting in the danger zone already. And so this is extremely high and would need some pretty specialized construction. And usually we assume that dams in the United States are constructed to really high standards and are being inspected carefully on a regular basis. And I guess if we assumed that, we'd be wrong, because there was a pretty spectacular failure last year. Here's a picture of, in my hydraulics class, I used to talk about dam failures in Zimbabwe, which is about one of the most poor and dilapidated countries in the world. They're suffering quite a lot from hyperinflation of their currency, and their economy's haywire, and so they can't afford to fix their dams. And so I used to be talking about dam failures in Zimbabwe, but now I can talk about dam failures in the United States. So here's Zimbabwe. All right, here's the Oahu Dam. It's in California, and just to give you an overview, here's the dam, and here's the overflow spillway. It's the same kind of thing where most of the time the water would come through a power plant, and it's just on very rare occasions that the water would need to go through this overflow spillway. And California's had a terrible drought for many years, but that drought finally broke last winter, and it was really wet in the spring. And what happened was they started sending water down that spillway, and ordinarily it's just, the water's falling down, it intercepts some concrete here, and there's a lot of rocks to help dissipate the energy at the bottom, and then it gets back into the river. But what happened was, over the course of several days, when they were sending water down the spillway, there must have been a little bit of damage or some weak soil underneath the spillway, or sometimes what can happen in previous cases, there was damage to a dam when the water was moving so quickly that it started to cavitate a little bit. Remember, high velocity means low pressure, and when the water has a really low pressure, then it can go below the vapor pressure of the liquid, and it can actually start to evaporate, go into the vapor phase. And so I'm not sure, I haven't followed the news too closely since the interesting picture stopped. I'm sure the engineering analysis of what went wrong has continued. You can see that what began as a relatively minor small hole, it got bigger and bigger, but they couldn't stop. They had to keep sending the water down that spillway because there was just no place else for the water to go. So they kept eroding this hillside, and they sent people down in there to inspect, and that gives you an idea of how big the hole was. Those are people, and so that was an enormous big hole, and it just totally destroyed this entire hillside. And this is the emergency spillway that water should never really have to go over that, because you've got this overflow spillway, but then the real emergency is, what if you have so much water that you can't send it all through the power plant, you can't send it through the overflow spillway, then you have to use this emergency spillway. And they actually did start sending water over that emergency spillway, and it started scouring this hillside. And that threatened the viability of the dam. Whereas this was never about threatening the dam, because the dam itself is pretty far away from this hillside that got scoured down to rock. So the dam, they say, was never threatened except for when they started sending water over this emergency spillway off to the side. So you can see it's taking a lot of sediment downstream. The color of the water couldn't be more distinct. It's, this brown color here means that soil is moving downstream, and there are a lot of fish farms and hatcheries for salmon, and downstream in this river they had enormous fish kills. Millions and millions of small fish were lost because the sediment levels interferes with their ability to respirate, and it kind of degrades the habitat and makes it so that fish can't survive. So there's the dam, the regular spillway, and this emergency spillway. And the emergency spillway has concrete just only on the part where the water is flowing immediately over, but then you notice that this is just soil hillside here. And that's what was scouring, is at the foot of that emergency spillway, the soil was being washed downstream once they started sending water over the emergency spillway. And they had to cut that off after just a couple of hours because they were worried that the entire dam was going to be potentially threatened if they didn't. So here's what it looked like as they were sending a little bit of water over the emergency spillway, and you can see that the soil is just being swept downstream. And people were making their projections about why the dam isn't threatened, why people don't have to worry too much, and there's a big rock ridge that separates where all the damage was from the dam itself. But people started to get pretty nervous once they had to use the emergency spillway. So reservoirs are interesting. We don't need to look at those. We could do that all day, right? Engineering failures are interesting to analyze. All right, the volumetric flow rate is the average flow rate multiplied by the cross-sectional area. And most of the time we'll omit the bar over the V here. That bar means average velocity. And the velocity can change across the cross-section. Here in this next slide, it shows that actually in reality, what happens is that we have a bullet-shaped velocity distribution, because at the center of the pipe, where we're the furthest away from surfaces that are exerting shear stress due to pipe friction, the velocity is fastest at the center and slowest at the edges. In fact, going down to zero right at the edge. And so here, this representation is saying, let's assume just a flat velocity profile that's representative of some average velocity across the entire area. And we can take that volumetric flow rate and turn it into a mass flow rate by simply multiplying the density of the fluid by the volumetric flow rate. And so if you consider the units there, we know that Q has units of cubic feet per second, or in SI it's cubic meters per second. And so then the mass flow rate, when we multiply the density by the volumetric, the mass flow rate will turn into mass per time. So it would be kilograms per second or slugs per second if it's the traditional units. So in other words, you can convert between mass flow rate and volumetric flow rate by simply multiplying the density by the volumetric flow rate. So this is assuming an average cross-sectional velocity. This is assuming that actually the velocity at each one of those cross-sectional locations is going to be a little bit different. And so the way that we could find the volumetric flow rate if we had an accurate description of the velocity profile is integrate over a lot of little differential areas the velocity that's representative of just a small section of the cross-sectional area. And if we follow a ring around, all of those velocities along the same ring are going to be the same. In the center, the velocity would be the highest, and it would be gradually decreasing as we get closer to the edge. But the idea is that we can integrate multiplying the velocity over these differential areas over the entire cross-section and find either the volumetric or the mass flow rate if we consider the density. Okay, so let's apply that idea of mass flow rate here, assuming that we have some average velocity, and instead of saying that there is a parabolic distribution of velocity, when you've got turbulent conditions and the flow isn't laminar, then this nice even profile kind of gets compacted down to where there's an average velocity that's pretty close to the actual observed flow velocity for the majority of the cross section, and then as you get closer to the edges, the velocity decreases a bit. Let's say that we have oil going through a pipe that's 50 centimeters in diameter, and we're given the density of the oil, and we know the mass flow rate. So given this relationship of mass flow rate is density times volumetric flow rate, for the situation that's described here, calculate the mean velocity and the volumetric flow rate. You always got to be careful on problems like these to make sure that the dimensions that they've given you matches the dimensions that you're going to need for the calculations. And so the diameter was given as 50 centimeters, but to calculate the cross-sectional area, you should be sure to convert that into meters because ultimately we want to have the volumetric flow rate in cubic meters per second. So you need to calculate the mass flow rate was given 550 kilograms per second, the density 850 kilograms per cubic meter. And if you cancel out the units there, you notice that the kilograms are in the numerator and the denominator, so they go away and it's just cubic meters per second for the volumetric flow rate. And then to calculate the average velocity, it's just the velocity multiplied by the area. So since we have the flow rate and the area, we can calculate the velocity is about 3.3 meters per second. All right, so chapter 5 is basically this idea repeated with combinations of other ideas that you've had before. And you can get an early start on the homework and really make a lot of progress because it's just mass flow rate and volumetric flow rate combined with ideas like Euler's equation or Bernoulli's equation or the hydrostatic equation. So it's not an easy chapter, but the base idea is fairly simple. Any questions that came up during this example? One of the things that the textbook talks about in chapter 5 is the idea of the control volume approach. And the control volume approach is just a really detailed way of accounting for flow and where it is at any given time. The idea is that we're going to be studying a system and its location in space over time. And so to do that, we can define a control volume that's enclosed by an outside control surface. And here you can see that the control volume can be irregularly shaped. It doesn't necessarily have to be a rectangular box. It can be shaped any way we like. And what we do in the control volume approach is keep track of the flow in and the flow out, and then try and assess if there's any accumulation of mass inside of the control volume. So some definitions are, first of all, the system that we study is a continuously connected mass of fluid particles. And it doesn't have to stay in the same location over time, but our system is just these certain particles that we've designated as part of our system, and anything that's on the other side of some artificial boundary is not within the system that we're studying. The control volume is an imaginary enclosed space that can rotate, it can deform, it can change its position, and the control surface is the outside surface through which we're monitoring whether the system is flowing in or out. And so ultimately what we want to do is find out what's happening inside the control volume by studying the flow in, the flow out, and then sometimes there will be reactions inside of the control volume where a certain constituent that we're interested in, especially in courses like environmental engineering, where you have maybe a chemical reaction that's breaking down a pollutant, or maybe even a microbial reaction, where there are bacteria that are breaking down wastewater, for instance. So the control volume approach is looking at accumulation of mass inside of a control volume. And so this is kind of the way that we can apply the types of problems. If we had a tank and there is a liquid flowing into the tank, that's what this pipe on the left-hand side is. This is our inflow tank, inflow pipe going into the tank, and then there would be an outflow pipe coming out of the side of the tank. Here we're distinguishing the system that we're studying with the darker blue marker compared to this lighter blue shading. It's some liquid that isn't a part of our system that we're studying at a given time t. So you'll notice that this tank is open to the atmosphere, and so it has a free surface of water. And at a certain time, there's a fraction of the system that's inside of the control volume. Now what we're going to do is look at some time increment into the future. At time t plus delta t, we're saying that the system's location changed over time. What you'll notice is that the water level, if this is in fact water, it's a liquid, the liquid level has fallen a little bit. And so it seems that less of the system is inside of the control volume, and so we have to account for that. If the system is constant over time, that mass can't be destroyed, and so we have to identify that during that delta t, the system started to flow out through the control surfaces. And so you'll notice this delta m out. It looks like the length of the liquid that's inside the outflow tube is longer than this segment of the system that was in the inflow tube at time t. And that may be why the liquid level is lower than it was initially, is that we had more flowing out than flowed in during the incremental time period delta t. So the idea of the control volume is that we're just going to do an accounting, a mass balance on this location of interest, and keep track of the mass inside the control volume over time and account for the flow in and the flow out. So here, this liquid could either exit the tank once it came in, or it could be stored in the tank. Those were the two locations that the incoming water could end up. The system stayed constant, but the location of the system changed over time. So symbolically, the way that we can represent that is that the mass of the system at time t was in the control volume, and then this amount that was about to flow in. And then at time t plus delta t, so later, there was still mass inside the control volume, and then there was the mass that had flowed out. The change of mass inside the control volume over time was the difference between the in and the out. And this is such a simple idea, but it can be used to solve lots of really complicated problems, especially when you combine mass with concentration. That's where it gets really powerful, is when you say that you don't have pure fluids like this, but you have mixtures of different fluids together, and keeping track of their location and the amounts over time is a really important application of the control volume approach. So here we're saying that this system is either accumulating inside of the control volume, or the difference between the in and the out. So the mass in the control volume over time is the mass flow rate in minus the mass flow rate out. And so accumulation is in minus out. Now, another thing that the book picks up on is the idea between the fluid properties that are transported with the fluid and those that are independent of a fluid's location and its motion. And the terms are: an extensive property is one that is proportional to the mass of a system, and so its properties move along with the fluid. And intensive properties are independent of a system's mass. And so, for instance, the viscosity of a fluid isn't affected by its location, and it isn't affected by how much of the fluid there is. If you have 1 liter of water at a certain temperature, it's going to have the same viscosity as if you had 100 liters of water at that same temperature. But extensive properties are affected by the quantity. So if you think about the mass of fluid or the momentum that it's carried when that fluid is in motion, those are each affected by how much of the system there is. So when it applied to the control volume approach, when we have a fluid that flows through a control surface, its properties are transported along with the fluid. And that's really important, especially when we're talking about power generation. Later in the semester, we're going to be figuring out how many watts of power can be extracted from a hydroelectric power plant. And so the moving water, over time, its properties are carried with that moving water. And so it still has the same amount of energy regardless of whether it's in the upper storage reservoir or as it's moving through the penstock and is being transferred into electrical energy. All right, so let's just get some practice with the control volume approach and thinking about in minus out. Now, we've already talked about the Oahu Dam, and the lake is upstream of the Oahu Dam. What I looked up for this example is the surface area of the lake. It's 370,000 acres. And I looked up the average depth of the lake, 63.5 feet. And so let's look at what would happen if we had that historical flow from June 2011 when it was 160,000 CFS being released from the dam. Let's say that it stopped raining, and we wanted to find out how long would it take to drain the lake if you've got this release of 160,000 CFS. And so what I'd like you to do, first of all, is begin a conceptual sketch. Read through the rest of this problem statement and try and identify the inflows, the outflows, and then the control volume itself is going to be the lake. But what we're going to be doing is figuring out how long it takes to drain that lake or empty the control volume based on the inflows and the outflows. Now, you're going to maybe need to search online for some units conversions, like I don't tell you the relationship between acres and square feet. Anybody here happen to have that memorized? Pretty close. You're on the right track. It's 43,000 something. Yeah. You can look up to get the rest, but yes, 43,000. I memorized it for, I guess, some obscure reason when I was a student, and it stuck with me. But you can look that up. Also, here it says that there's an upstream dam that's releasing 13 million pounds of water per minute. So maybe you remember how many pounds of water there are in a cubic foot, but if not, you can look up those either in the fluid properties in your book or online. I've got a handout I'm going to give you. We'll pause the recording here, give you some time to collaborate with your classmates and figure out how long is it going to take in days to drain that lake. You know, if we represent this reservoir as some sort of a volume, you know, just simplify what it actually looks like. There's the two flows in, one flow out. We know the cross-sectional area of the reservoir and its depth is given. Now, there's several simplifying assumptions here, and one of them is that the cross-sectional area is constant as the water level falls. In reality, that's not true. When the water level falls in a reservoir, the cross-sectional area decreases because they have kind of like a trapezoidal distribution on the side slopes of it. This is assuming that it's basically the side slopes of this reservoir are vertical, so that as the water level falls, we have the same cross-sectional area. But in any case, even if that wasn't true, in the real world, there are curves that relate the surface area and the depth so that you can calculate the overall volume of a reservoir. And that's what we really need, is we need to know how much water is there, because there's more flow going out than is coming in, and that allows us to calculate like the net outflow, and then the amount of time it's going to take to drain that volume of water is going to be related to the net outflow. Let me try and make this a little bit bigger in case there's still spots you need to see. So the outflow is just given directly, that 160,000 CFS. The inflow in stream 1 is just area times velocity. That was relatively easy, you know, just the continuity equation there. The stream 2 was, we had the mass flow rate, pounds per minute. And so we need to convert that to a volumetric flow rate and then convert the time from minutes to seconds. So it's kind of a two-step process there, assuming that we've got 62.4 pounds of water per cubic foot. That's kind of a typical value for water. So looking at the differences there, the outflow is 160,000, inflow 1 is only 1,190, inflow 2 is only 3,472, so there's a big difference there. The net outflow is more than 155,000 CFS. Even though we still have some water coming in, there's a lot more water going out of the reservoir than is coming in, and so that's why the water level is going to be decreasing. If we wanted to, we could calculate the velocity that the water level is going down. The approach that I used, I just calculated the time, but sometimes if you've ever filled a swimming pool before, you know that that is a very tedious process, because if you're using a hose to fill a swimming pool, it's going to take a really long time. And you sit there and you watch it and you watch it, and it seems like the water level isn't changing at all, even though you're continuing to add the water. And so here, if it's taking 76 days to fall a distance that is, what's the depth? 63.5 feet. So it's going down less than a foot per day. That's the speed that it's falling downward. We could calculate the velocity that the water surface is declining. But this approach, all I did was I said, we've got a certain volume of water. The reservoir volume is about 1 times 10 to the 12th cubic feet. Got that by the area of the reservoir and its depth. And so if we divide the net outflow rate by the volume, then we can find out how many seconds there is, and then there's 86,400 seconds in a day, so then it turns into 76.3 days it should take to empty. So a couple good questions as I was walking around. Someone said, well, wouldn't the outflow rate decrease over time? Because, you know, as that water level gets lower, then the stream of water that's shooting out is going to decrease. You know, at first, when you've got 63 feet, it's going to be coming out of that hole with quite a lot of pressure, so the velocity is going to be quite high. And that's true. Unless we had some sort of a valve here that was limiting the flow rate out from the very beginning. You know, it might have been that it would have been flowing out even faster if those gates hadn't been regulated somehow. But more realistically, yes. As the water level falls, then the outflow rate would decrease. It's just 160,000 CFS right now. And so what would that do to our estimate? If the water level decreasing slows down the outflow rate, would that increase the amount of time it takes or decrease the amount of time it takes? It's going to make it even longer because the outflow rate would be declining. And so this is actually a best case scenario, that it takes 76 days. And so that seems like a lot of time, and it is. You know, to drain a reservoir of that size, even though we're talking about a huge outflow rate of 160,000 CFS, and we saw the video, and there seems like enormous quantities of water through 19-foot tall gates. Still, 76 days, and that's the best case scenario if we can maintain that 160,000 CFS during the entire period. Now, we wouldn't drain that reservoir all the way to empty. What would be the point of that? You know, you kill a bunch of fish and you lose your pool so that now people can't boat, and so it's just maybe a hypothetical what if to illustrate more broadly the idea of the control volume approach. You've got some tank that you're studying, and you're looking at the in and the out, and the difference between the two in this case was a negative accumulation. All right, so yesterday I sent an email with the YouTube link. Raise your hand if you got that email. All right, I won't ask you if you've watched the video yet, because you've still got a little bit of time. You've got between now and 2 o'clock for the earliest of you. It's a 10-minute video. It'll give you a really good idea of what we're doing today, what the equipment looks like. When you'll really appreciate the video, I think, is when you're actually starting to do the calculations, because it's a little bit abstract what we're going to be deriving from the experiment today. But it's all about water flowing out of an orifice. And so I'll see those of you who I've got for Tuesday lab this afternoon, the rest of you tomorrow. Have a great day.